Hello there. In this video, we will talk about something called related rates, which is our last section in chapter 2. And it's basically an application to implicit differentiation, which we discussed in section 2.7. So if you haven't yet looked at that, math tends to be, build on itself sequentially. So please go watch 2.7's videos before trying to think about related rates. Just to give you a brief of an overview about what this section is and stepping back a little bit and just remembering what we're doing in general with this class as a whole. Differential calculus, which is what we are studying. There is another branch of calculus called integral calculus. That is what you would typically take in the second semester of calculus. So if you take APM 106 or Calc 2. Differential calculus studies derivatives, and derivatives tell us how things change. So differential calculus is really the study of rates of change. So we, for the first time in your math career, kind of look at how things change with respect to one another, and not just kind of seeing statically, like what's y when x equals 2 or something like that. We're saying how is y changing when x is 2? Like how are these two things, their change related to each other? So these are words that we'll actually start using a lot more in chapter 3 and look more broadly about what the derivative can tell us. Things change in various ways. So you could have something that's increasing, we could have something that's decreasing, we could have something that's shrinking or growing, and just to keep them consistent, right? Shrinking goes with decreasing, growing goes with increasing. And there's a lot of other words, right? So just put etc. In most of the time, things change over time, right? I mean, almost everything is changing over time. So in related rates, we're going to be talking about derivatives with respect to time, right? So change of a quantity occurs over time. We want to then, if we're going to talk about the rates of change of something over time, right, that's the derivative is rate of change. But now our input variable is always going to be t, or time, or at least maybe not our input variable, but the thing that we want to find the change with respect to. Okay, so the fact that we are going to be looking at changes over time, this tells us that we want to find the derivative with respect to time. And we normally use a little t to indicate our variable for time. Mathematically, this would look like not d dx, but d dt. Okay, there's the with respect to time part. And then with, whatever we have as the thing that we're finding the rate of change of. So in other words, we could say d quantity, whatever that variable is that we're looking at changing, the rate of change of, over dt. So just hold on for a second, that's a little confusing. Let's look at some examples. Just getting used to thinking about these symbols a little more broadly as a symbol that means rate of change. I know we've talked about rate of change in a couple different ways with average and instantaneous. This is related, but a little bit different. Okay, so let's write the following statements mathematically. Number one, we have a tree growing 1 foot per year. So we need some variables here. The growth of a tree is normally like its height, right? So let's call little h, we'll call that the height of the tree. And then we have time, which we'll call that little t, and that's in years. So we don't actually know the height at any time. We're not actually even focusing on what is the height. We just know the growth. So this is the change in the height over time. So we would say then dh dt, okay, that means the change in the height with respect to time, so over time. That is increasing because of growing. So it has a positive rate of change, and it'll be 1 foot per year. So that's how we would translate this into a mathematical symbol. Okay, so this sentence of a tree grows 1 foot per year, that whole thing can be kind of neatly written and condensed in this way of dHdt equals 1 foot per year. In example 2, we have the radius of a tree increases 0.2 centimeters per year. So now that's not the height, that's the radius of the tree, right? So from the center of the tree out to its outermost layer of bark. So we will have a variable now, radius, so we will call that little r. It's still per year, so we'll call little t in years. The rate of change of the radius will be dr dt now. So it's the d quantity, d whatever, over dt. And again, since it's increasing, then we have a positive rate of change. And so the rate of change of the radius is 0.2 centimeters per year. And so again, this whole sentence here can just be rewritten in math notation as dr dt equals 0.2 centimeters per year. Okay, in example 3, we have the outside temperature drops 5 degrees per minute. Getting pretty cold pretty quick. Every minute, 5 degrees, we're losing. So here we've got things that are changing over time, and that thing is temperature. Right, so I would call big T temperature, and then little t will be minutes. So we have the change temperature over time in minutes, right? So we'll do d big T over d little t. That would be the change in the temperature with respect to time or over time. Now, because the temperature in this example is dropping, right, the rate of change, we would interpret that as being negative because the temperature is decreasing or getting lower, getting smaller. Whereas in examples 1 and 2, the radius and the height were increasing or getting larger. So we have to interpret that as the rate of change being negative, so this comes from the dropping, negative 5 degrees Fahrenheit per minute. And again, this whole phrase here can be represented by this dt, d big T, d little t, equals negative 5 degrees Fahrenheit per minute. Now, these aren't related rates problems yet. I just wanted us to get used to kind of knowing what these symbols mean and getting a little bit of practice translating these because it's a lot to do all at once. So these are not related rates problems just yet, but these are pieces that we'll see in related rates problems. The notation can be a little tricky. So in example 4, we've got a balloon deflating at a rate of 3 cubic inches per second. Okay, so the balloon deflating at a rate of 3 cubic inches. Now, cubic units represents a 3D, like a 3D measure, so volume, right? So the 3 cubic inches per second, that's talking about volume changing. So let's say V equals volume. I'll have T, little t would be in seconds. So then the rate of change of the volume, say dV dt. Okay, we've got the balloon is deflating, so it's losing volume. So again, we have to interpret this as a negative in its rate of change. So negative 3 cubic inches per second. Okay, so again, that deflates, gets translated into a negative rate of change. And so again, this whole sentence, a balloon deflates at a rate of 3 cubic inches per second, can be rewritten in this cute little notation of dV/dt equals -3. Okay, so let's move on to actually talking about how to solve related rates problems. We're gonna basically have 2 keys to solve them. And the first one is to really understand that we are taking the derivative with respect to time. So we're always looking at things changing over time in related rates problems. Okay, so one key is to understand that we are taking the derivative. I know we haven't found any derivatives yet or taken any derivatives, but we are going to want to be talking about rates. And so that involves derivatives. Okay, so eventually, like ultimately, we are going to be finding derivatives. So we want to always be taking the derivative with respect to time, little t. So we will always represent this as little t. So we'll always have a d dt. Now in our formulas or equations that we'll start with, if you just look down at these examples here we're differentiating with respect to time t. But if you notice in the equations, we actually don't have a variable t in there. That is how it's always going to be. So we're going to look at just basically we have 2 quantities that are related in general. So for example, area and radius of a circle. That means that if their quantities are related, then the way that they change will also be related over time. Whether the way that they change over time will be related. So because we don't have little t's in any of our equations that we're going to be finding the derivative of, we've got to do implicit differentiation on every single variable that's present. Okay, so we have to, huge thing here, is that every single variable, since there will be no little t in our equation, and we actually don't need it, every single variable needs to be differentiated implicitly. Okay, so let's just take, again, these aren't related rates problems, but let's just see how that might look. In our first example, we're going to differentiate x squared plus y squared equals z squared. So this is a variation or like a version of the Pythagorean theorem. So if we were going to find the derivative now with respect to t of both sides, that's something we can definitely do. Right, we've done this with respect to x when we have x's and y's mixed up, or an implicit equation like that. And so we're just really like generalizing this procedure and saying, well, we can do that to both sides. We're going to differentiate now with respect to time, though. So if you can imagine, I don't know, we have a right triangle here. We've got x, y, z. Maybe the lengths of the sides, like this is in motion. So the lengths of x and y are getting larger, or maybe one's shrinking and the other one's getting larger. Then that forces z to also change the hypotenuse. And so if we only can start with this relationship, and we know how these things are changing over time, then their rates of change will be related too based on their initial relationship. So we will differentiate the x squared. Now we're differentiating with respect to t. So x squared gets to be differentiated like usual, like we get 2x. But the x and the t aren't the same variable. So we've got to multiply this by dx dt now. Okay, so it always stays same here, like it's dt, dt, and then because we had x's here, that's the variable that we're basically multiplying by the derivative of the inside, which is x, but with respect to time. So this is just the rate of change of x over time times the derivative of x squared. Okay, then we'll add the derivative of y squared. So that will be 2y. But then we got to multiply this by dy dt, the rate of change of y over time. Okay, so we've got y here, so we need dy dt multiplied by the derivative of y squared. Then on the right-hand side, the derivative of z squared will be 2z, but then z is not t. Again, on the right-hand side, we're doing dt, so we need a dz dt multiplied, the rate of change of z. So right, we have z here, so we need a dz and then dt. And that's basically the end for now. We differentiated with respect to time, so that's all I was trying to ask us to do here. So this right here is called the related rates equation. Okay, this last thing that we've got here, this is called the related rates equation. And it's based off of the equation that we started with, right? This is the original just equation that relates the quantities. So this one doesn't relate the rates, this one relates their actual amounts, but they're related, right? The original one gives rise to an equation that relates the rates of change of each of the variables. That's the whole point of this. So ultimately, with a related rates problem, what we're going to have is values for maybe x, y, z, and then also one or more of the rates of change. And then we will use our related rates equation to find how something else is changing over time. So let's look at the equation a equals pi r squared. So of course, we know this as the area of a circle. So if you can imagine that we have something circular that is increasing with time, like maybe an oil spill that's forming, like it's dripping in the center, and then it forms, just goes out into a flat circle. And over time, the radius is increasing and the area is increasing. Right, so the way that the area and the radius are changing are related to each other based on the way that their quantities are related. So if we're going to differentiate this with respect to time, we'll differentiate the left-hand side. So we'll have d dt of a equals, and then we'll also differentiate with respect to time the right-hand side. So d dt of pi r squared. Now on the left-hand side, the derivative of a with respect to time, that's just, 1, but then times dA dt, or it's just dA dt, right? This is just like a variable to the first. It's capitalized, doesn't matter. If this were just x, right, its derivative would be 1, but then because this is all implicit, because we've got dt here, we have to multiply by the rate of change of a. Okay, so this will be dA dt, or 1 times dA dt. Okay, then on the right-hand side, we've got pi. Pi is a constant multiple. I know it looks like a variable. It wants you to think it is, but it's always just a constant. So that's going to stay and multiply by the derivative of r squared, which would be 2r. But again, every variable is needed to be differentiated implicitly. So because we differentiated r and we're differentiating with respect to time t, this means it times the derivative of r, so times dr dt. So if we're just gonna like kind of write this a little bit better, we would say dA dt equals 2 pi r times dr dt. Okay, and so this here is the related rates equation, or the equation relating the rates. Okay, and this one I can kind of give a little bit of, like, can kind of make sense of, hopefully. So if you have a circle and its radius is getting larger, so expanding out, you would get another larger circle. And so this is the rate of change of the area. This is the rate of change of the radius. 2 pi r is actually the circumference of a circle, right? So what this is saying is that the area that you add on, if over time, would just be basically like another little layer out here that's equal to the circumference, but then multiplied, so the thickness would be how fast the radius is going outward, and that would tell you the rate of change of the area. Okay, so that's the first key, is to remember everything is differentiated implicitly with respect to time. The second key to related rates problems is that you have to understand when you can substitute in numerical values. There are some that you can put in before differentiating, and there are some that you have to wait until after. Okay, so you have to, key number 2, you have to understand when you can substitute in numerical values. So there are two options. One is before differentiating, and one is after. Okay, so the ones that you can put in before differentiating are the ones who don't have a rate of change. In other words, they are things that are constant or don't change over time. However, if you have something that is changing over time, you want to differentiate it and get its rate involved, because if it's changing, it's got a rate. So those would be the things that you would wait until after you differentiate to plug their values into. So before differentiating, again, these are things that are constant or that do not change over time. So if you have any situation where there are some variables that actually aren't variables, maybe that's not a great way to put that. Let's say quantities, because variables kind of implies that it varies. So let's say quantities that are constant. Do not change over time. Okay, the ones that you have to wait until after you differentiate, and these are things that have rates of change over time. So these are things that do change over time. So these are variables that do change over time. Okay, now I know we haven't gone through an example with this, so you might not know exactly what I'm talking about with these two keys here. But as we go through, I've got basically, I think, 5 examples that we'll work through. We'll do one video each on them because they are kind of long, so you might want to split it up a little bit. But make sure that you have these keys next to you, and the notes that you took next to you while we're working through them, so that you can kind of piece together like exactly what I'm trying to say here, because I think it'll make more sense once we go through an example. So tune in to our next few videos, which will go through several different situations with related rates. They're going to be super fun. These are really cool problems, and I'll see you then.